Hello everyone. In today's session, we are going to learn about outlier analysis in R. An outlier is a data point that is very different from the other observations in a data set. In this session, we will learn how to detect, visualize, and remove outliers using R programming. We will mainly use functions such as boxplot, boxplot.status, and hist. We will also learn the IQR method, which is one of the commonly used statistical methods for identifying outliers. Outlier detection is an important step in data pre-processing and statistical analysis because unusual values can influence our analysis and machine learning models. Let us first understand what an outlier means. An outlier is a data point that differs significantly from the other observations in a data set. There can be different reasons for an outlier. Sometimes it may be caused by a data entry error or measurement error. In other situations, it may represent a genuine but rare event. Outliers are important because they can affect our analysis in several ways. First, they can distort the shape of the data distribution. Second, they can change statistical measures such as mean, variance, and standard deviation. Third, outliers can influence machine learning models and may reduce their ability to generalize to new data. Therefore, detecting outlier is an important part of data pre-processing. Now let us see how we can create a data set containing artificial outliers in R. The first step is to generate normal data. We use the R norm function to generate 500 observations from a standard normal distribution. The code is data hyphen R norm of 500. Normally, values from this distribution will generally be close to 0, typically within approximately -3 to +3. Next, we deliberately replace the first 10 observations with extreme values. Say, for example, we have values such as 46, 50, -90, -82, and 74. These values are intentionally introduced so that we can demonstrate how R detects outliers. So in this example, the dataset contains 490 normal observations and 10 deliberately inserted extreme values. Now that we have created the data, the next step is to visualize the outliers. For this purpose, we use the R function, boxplot of data. A box plot provides a compact summary of the distribution. The box represents the middle 50% of the observations from the first quartile or Q1 to the third quartile or Q3. The line inside the box represents the median. The whiskers extend to the most extreme observations that are still within 1.5 times the IQR. Any observations beyond the whiskers are displayed as individual circles. These circles are potential outliers. In our example, we can clearly see values far above the below the main group of observations. Therefore, a box plot gives us a quick visual method for identifying outliers. After identifying the outliers, we can remove them from the dataset. R provides the function boxplot.status to identify the values that it considers outlier. The code used here is new data of not data percentage symbol in percentage symbol. Boxplot.status of data dollar symbol out. Let us understand this carefully. Boxplot.status of data dollar symbol out returns the values identified as outliers. The expression data in checks whether each value belongs to that outlier list. The exclamation mark or not means not. Therefore, the code keeps all values that are not identified as outliers. After removing them, we use box plot of new data. to verify the result. If the removal was successful, we should no longer see the outlier circles beyond the whiskers. Another useful visualization technique for detecting outlier is histogram. In this example, we first set the random seed using set.seed of 123. This ensures that the random data can be reproduced. Then we create a dataset containing 1000 normally distributed observations and deliberately add 4 extreme values 10, 15, 12, and 100. We then use hist of data to display the distribution. Most of the 1000 observations are concentrated around 0. So we see tall bars around the center. The artificially inserted values are far to the right and appear as isolated bars. This separation from the main distribution provided a visual indication that these observations may be outliers. So, a histogram provides a complementary method to a box plot for understanding unusual observations. Now, let us move from a single variable to a dataset containing multiple columns. The presentation uses three variables named x, y, and z. For example, the x column contains values such as 12 and 15, while the y column contains values such as 25 and 77. The z column contains extreme values such as 48 and 90. To identify outliers, we use the interquartile range or IQR method. First, we calculate IQR equal to Q3 minus Q1. Then the upper limit is Q3 plus 1.5 multiplication IQR. And the lower limit is Q1 minus 1.5 multiplied by IQR. Therefore, a value is considered an outlier when value greater than Q3 plus 1.5 multiplied by IQR or value less than Q1 minus 1.5 multiplied by IQR. The important point is that each column has its own distribution. So the IQR calculation is performed separately for each variable. Now we can visualize all three columns together using box plot. This produces three box plot side by side. Let us examine what we can observe. For column X, the values 12 and 15 are above the whisker. The column Y, values such as 25 and 77 are identified as extreme observations. For column Z, values 48 and 90 are far beyond the normal range. An important advantage of using the IQR method is that each column is evaluated according to its own distribution. Therefore, we don't have to use one fixed threshold for every variable. This is particularly useful when different variables have completely different scales. Instead of writing the IQR calculation repeatedly, we can create our own reusable function. The function is called detect underscore outlier of. Inside the function, we first calculate Q1 using the 25th percentile. That is Q1 goes to quartile of x comma 0.25 comma na dot rm equal to true. Then we calculate Q3 using the 75th percentile. Q3 which represent quartile of x comma 0.75 comma na dot rm equal to true. Next we calculate IQR equal to Q3 minus Q1. Finally, we check whether each value is above the upper limit or below the lower limit. The function returns a logical vector. That means it returns either true or false for each observation. True means that the observation has been identified as an outlier. False means that it is not identified as an outlier. Creating a function like this makes our R code reusable and easier to maintain. Now we will use our detect outlier function to remove outliers from multiple columns. For this purpose, we create another function called remove underscore outlier. This function accepts two input, the data frame and the columns that we want to examine. The function uses a for loop. For each selected column, it calls the detect outlier function. rows containing an outlier in that particular column are removed. In this example, we apply the function to x, y, and z. The result is a new data frame containing only 5 rows. The original dataset contained 11 rows. After removing rows containing flagged values, only the rows without an identified outlier in any of the selected columns remain. Please observe one important thing here. We are not simply deleting individual cells. When a row contains an outlier in one of the selected columns, the entire row is removed. For example, if a particular person's age is a normal but their income is identified as an outlier, removing the row will also remove the person's other valid information. Therefore, in a real world data set, we should not automatically remove every outlier. We should first investigate whether the value is an error or a genuine observation. This is especially important when working with medical, financial, scientific, or engineering data. Finally, let us summarize the important R functions we learned today. For generating sample data, we can use R norm of n. This generates n values from a standard normal distribution. For visualizing a single variable, we can use box plot of x. It displays quartile, whiskers, and potential outliers. For understanding the overall distribution, we can use hist of x. A histogram shows the frequency distribution and can help identify isolated observations. To obtain the actual outlier values, we can use boxplot.status of x dollar symbol out. To remove outliers from a single variable, we can use x not x in boxplot.status of x. And for multiple columns, we can use the reusable remove underscore outlier of df comma columns function. So these functions give us a basic toolkit for detecting, visualizing, and removing outliers in R. So let us conclude today's session. Outliers are observations that are significantly different from the majority of the data. They can affect the distribution of data and influence statistical measures and machine learning models. In R, we learned several ways to identify them. We used box plots to visually identify observations beyond the whiskers. We used histograms to identify observations that are isolated from the main distribution. We also learned the IQR method, where observations below Q1 minus 1.5 times IQR or above Q3 plus 1.5 times IQR are flagged as outliers. Finally, we created reusable R functions to detect and remove our outliers across multiple columns. However, remember that an outlier is not automatically a mistake. Before removing it, we should investigate the reason behind the unusual value. That's all about today's session. Thank you.